mixture. But we can actually sit in the hour. The votes are in, so I want to congratulate. So let's see if I can get this down a little. And then we had Granny got retweeted by David Lee himself, who is the PI for that Granny knot. So that was actually kind of cool that he acknowledged that. I got Maya's permission to post that, of course, but he has a good sense of humor, and I think that he actually would appreciate that. So just thought you would like to know that that was something he is aware of, and he acknowledged it. So AM Lab, that was the super benzene. Many congrats to them. And PM Lab, that was the granny knot. So well done, guys. Honestly, it was very close. You guys all did great. That was really exciting. So you can collect your prize and workshop and bring them there. Okay, so back to business. Aldol reaction versus condensation. So we have been doing the aldol chapter, and we're kind of deep into it now. It's a hefty chapter, aldols and enolates. We will be, I'm trying not to go too fast, but as there's a lot of material. The aldol reaction itself is where basically what we covered today. We're going to do some focus on condensation. Then we're going to start mixing up the reagents. So it's not, remember I kind of likened it to, they're like one turns on itself, sort of like, if you watch Walking Dead or something like that, but it's kind of like, this is how it starts, but then once it's bit by the base, it turns on its own time, but not, not the enolate, they'll turn on the original. And so they'll self-react to form the beta hydroxy ketone. So you have one that is left intact because it had the enolate. The other one got attacked and opened to eventually be a protonated alcohol. And so the R groups are dependent on what the R groups were here. So 2 methyls, right? So the carbon count remains the same, 3, 3, and then 6. And so, but it can continue to react. There's certain conditions that favor this. In fact, the vast majority of them will continue to react with any heat and produce a alpha, beta, unsaturated ketone, which we've looked at the last material. And the exams are almost done, graded, but this is one thing I noticed was something I guess that hasn't stuck yet. A lot of people missed the one where with the alpha, beta, unsaturated carbonyl, because we only did one reaction with that one, and that was the Gilman adding the 4 position. But that's coming up as a big theme in this chapter. There's a reason we named it earlier and introduced it, even though it seemed a little peculiar. Add a group here. That's going to be a big focus near the end of this chapter. So it's important that we are able to make them from an aldol addition followed by condensation. Condensation, remember, means lose water. Then we have our conjugated pi system, and this is favored even more if there's extended conjugation. So there's a minimum of 4 conjugated atoms in this, but it's favored even more if the R groups have more conjugation to allow. So sometimes it's called an enone because it's it's such a commonly occurring set of functional groups, the alkene next to the ketone, that we will want to be able to recognize that pattern. So the condensation, if it's a favorable condition for it to do so, it just goes straight there. This is an intermediate. In other words, it doesn't stop there. So we will visit that very reaction right here on page, let's see, where are we, 100. And what I want to show you is just to remind you what we did. The aldol addition stops at so that's what the previous slide summarized. They stop at the beta hydroxy carbonyls. That was the previous lecture for the most part. Okay, but if we're going to go on to do a condensation now. that previous slide, I know that wasn't in your reader. Those are on Canvas as a PDF file. If you feel like you want to take further notes on them, you can always print them out and bring them, or you can just print out what you feel like you would have liked when you get home. The condensation is also called the dehydration, because remember, condensation reactions are the loss of water. So it's not, the reaction's not done, it proceeds to alpha, beta, unsaturated carbonyl. So it could be a ketone, aldehyde, that sort of thing. So in other words, look at the language of this question. We're going to draw the mechanism, just because we're kind of revisiting that, and predict the dehydrated product. That means we're not stopping at the beta hydroxycarbonyl. We're going to predict what happens if we keep going. So, from the previous lecture, we have our base, and we also have our alpha carbon. Is this an alpha H? No, that's aldehyde is attached to the carbonyl. It's not acidic. You have to look for the carbonyl carbon, then look for an alpha carbon. No alpha carbon there. There is an alpha carbon there. So that is an H that we may remove, and the only H that we may remove. So then we have our, look for a base to do that for us. And so hydroxide is the base, and we make our enolate. So then remember that our enolate attacks, when we're doing a self-addition or self-condensation, it attacks one of the original starting materials that has not been deprotonated yet. So this is our nucleophile, this is our electrophile. So the lone pair attack, open, and so the new bond is between the alpha carbon and the carbon that was part of the carbonyl. So I'm just going to scoot everything over, put the left one on the right. So this is my aldehyde that used to be an enolate. That's the aldehyde side, so that was that nucleophile. And on that carbon, it's making a bond. The reason I put it on the right is so it can actually make a bond on the left. It's making a bond to, here's a new bond. It attacked the carbonyl carbon, which opened up. And there was an H from the aldehyde and a methyl. All right, and then of course we protonate and we're done with the addition only. So I'm not going to belabor this mechanism every time, but I'm only doing it because we didn't do it since last lecture. Okay, so there's our alpha, beta, let's see, where's my beta carbon? Alpha, beta, so there's my beta hydroxy carbonyl. So beta to the carbonyl is a hydroxy group. This is the aldol addition product. But it's not done, it says to do the dehydrated product. So dehydration, that means we lose water, and we know we're going to get an alpha beta unsaturated carbonyl, right? So this is an aldehyde in this case. So that means on the alpha carbon, we need to lose the H to make the alkene. So we do basically a type of elimination. And the alpha beta unsaturated carbonyl is our dehydrated product. Alpha looks funny. There we go. So as you can see, water is gone. We lost the OH and the alpha H that was there, that was drawn in. So the green box illustrates our dehydrated product. Okay, so a lot going on there. If you're asked to do the aldol addition, it's that intermediate. Yes, Valley?
Will it always favor the less direct conjugation of one?
It always favors the conjugated double bond. It's always going to be alpha beta. It's a good question. Conjugation is going to be what determines all of that. Okay, it's going to favor the conjugated. So it's always going to be alpha beta. Okay, so I'm going to try to do this without the mechanism for one more example, but you can fill in the mechanism for practice. Yes?
Sir, can you slide it up this?
Sure.
Thank you.
Okay, so for the second example, I'm just going to try to, instead of getting through all the specifics of the mechanism, I'm going to try to reason with the mechanism to predict the product. So it says dehydrated. Okay, you might want to draw the intermediate to get there, but let's see if we can kind of walk through it. Okay, so we know in an aldol reaction, the first step is the enolate, which means that there used to be an anion right there, right? So that's where the negative charge is. So one of them stays intact, so you could start by drawing the starting material as is. That's the easiest part. And then you need to draw your new bond because it attacked something. So there's the new bond. Okay. Then from here you got to put some thought into it. I actually think it's easiest to reason through the mechanism by drawing the addition product first. So that's the only intermediate I'll draw. So this is the new bond. Then what happened? This attacked that. So it's new bond to carbonyl carbon. Carbonyl carbon's open. And I need to draw my two R groups. All right, so I'll repeat that. New bond to carbonyl carbon. Carbonyl carbon's open to an O minus, which I'm just going to go ahead and move straight to the OH because it gets neutralized. And then my two R groups. So CH3, and then I'll put phenyl for my other R group. So when I'm done, if I did my aldol addition properly, I have a beta hydroxy carbonyl. I do, right? So this is an intermediate. This is the addition product. But now I want to draw the dehydration product. From this point, I think we can draw everything out. We know that we have to lose water and have an alpha, beta, unsaturated carbonyl. So that means that these are going to be gone. This is my water loss here. Now, I'll stick to the major being, I think Valerie was also alluding to the sterically hindered issue. Now we have to think about E versus Z, right? So, as usual, the less sterically hindered is favored, so that usually means E, because the bigger group is usually higher priority, not guaranteed, but you put the big groups trans to each other, in other words. Okay, so once again, this is where the hydroxy used to be. Lost it as water. Two R groups are there, methyl and phenyl. That's my dehydration product. And that's the final answer. Okay, so naturally, since we spent a good deal of time just drawing the addition product as it was, question always comes up. How do I know if I can stop with the addition product. Sometimes you'll be asked to draw the dehydration product, sometimes you'll be asked to draw the addition product, sometimes you'll be doing homework, you look in the back, and you drew the dehydration product, but Klein drew the addition product. It's a spectrum of what's favorable, right? So you have to evaluate the conditions. So we're gonna do that out here, right? With some of these words kind of ready for you. Usually heat promotes the dehydrated product, drives off the water, right? If, this is an important one, so this is telling us that heat will favor dehydrated. If the alpha, beta, and saturated carbonyl formed when the aldol product is dehydrated is conjugated to anything else. So remember, it's already conjugated to 4 atoms, no matter what, because the definition of an alpha, beta, and saturated carbonyl, so we would have R, for example, that's the minimum for alpha, beta, and saturated carbonyl. And then it's conjugated to 4 atoms. But let's draw another R group, R prime. So 4 atoms conjugated. That does not mean it's conjugated extensively, right? So we say it has extended conjugation if you go beyond 4 atoms, because by definition it already has 4 atoms conjugated. If R prime can be conjugated to number 4, then we have extended conjugation. Okay, so if R prime, when it gets attached, we did look at it and we discover, hey, it's even more conjugated now. Do you think it's going to favor addition or dehydration? Dehydration, because in the addition product, there's no conjugation. By dehydrating it, you create a conjugation path. So let's take a look at these 2 examples. Here's my addition product. Oops, it's a little bit low. Addition product. What happened when I put them together? So I got 4 atoms conjugated, 1, 2, 3, 4. I did not create extended conjugation. Methyl did not do anything like that, right, to promote that to go further. So in that case, I would probably, on my old exams, just to make it extra clear that I want you to draw that, you would either have the words, same dehydrated product, or you would even have heat added over it to promote, to indicate that you're going to keep going. If you don't see heat, you don't see extended conjugation, you could very well stop at the aldol addition product. So what's going on here? Heat's not added over the arrow. It doesn't need to be, because the driving force for continuing is, look at this R group. It's a benzene ring. So we have, and over here as well, we have a lot of atoms conjugated, way more than 4. So we have extended conjugation. So that's going to favor your dehydration product to be the major path. Okay, so that's what this little side note gets to about extended conjugation. Okay, so if the last point to work through to decide which route you're taking, well, in the same path is how far in the path you're going, right? If you're stopping at the addition or if you're going to keep going to the dehydration. If it's not conjugated to anything else, right? And if there's no heat especially, right? Then you're going to allow the dehydration to be the minor product. So there's no driving force for it to lose the water. It's basic conditions. It's a little hard to drive off OH minus as a leaving group, right? So you've got this interplay of what is the better scenario? Have a bad leaving group form, right? Or have a more stable product form. We're trying to just draw a line in the sand here, to be honest, because it's really a big spectrum. So if there's no heat and there's no extended conjugation, you're in the gray area. Sometimes it's actually really a mixture. So you have to do something to really disfavor the formation of the dehydrated, because you'll actually really see dehydrated form almost no matter what. So we'll just assume it to keep it simple, that the major product will be the addition product unless it's spelled out for you that heat is explicitly stated or extended conjugation is found in the dehydrated product. So if you are not sure which way to go, look for heat over the arrow. Look for the words used to describe the problem. Oftentimes it'll be simpler than you think. They'll tell you, draw the dehydrated product, draw the aldol addition product. You have to know that vocabulary. Draw the alpha beta unsaturated carbonyl that results. That means you're doing the dehydrated route. Draw the beta hydroxy ketone that results. That means you're doing the addition route, right? So pay attention to language, pay attention to what's over the arrow, and pay attention to the nature of the final product. If you extend the conjugation, then yeah, dehydration is going to be key. Usually there's a lot of clues that will, because it's a spectrum, most problems are designed to kind of, if you studied it, it'll be slapping you in the face which way you're going. It'll be heat or vocabulary used, so just pay attention to that and that should actually work out in your favor. Because we're making larger molecules with this, sometimes the retro analysis can feel a little bit tricky. So I'm going to look at an example of, we'll go backwards now. So, okay, here's an addition product. Can we draw what it started from? What were the starting?
I have a quick question.
Yes.
What was supposed to be in that blank?
Yeah. If it's dehydrated, it's major. Thank you. All right. I think I said it, but didn't write it. Okay, so let's do some one step backward thinking. So we have to figure out what this used to be. So in other words, we should have the enolate plus the carbonyl, right? So aldehyde looks like we had. All right, so notice I knew it was an aldehyde because I had this piece, and so far we've only done self-condensations or self-additions. So they're going to be twins basically, except for one's going to be the enolate of the other. So I noticed that I have an aldehyde that could not have been removed, right? So I must have used this alpha carbon to attack that carbon. Makes sense because that used to be a carbonyl, right? It's an OH now. So this used to be the carbonyl, and so the aldehyde that it used to be can be kind of illustrated if you choose to draw on the H. So in red, I will circle, this is what starting should have been, right? Because it attacked here. This is where. So that is what the aldehyde should look like, right? And then our new bond, right there. That was from the nucleophilic attack. So my aldehyde, let's see, so I have 1, 2, 3, 4, 1, 2, 3, 4. And because we've only really done self-condensations, it's pretty simple to write out the enolates, the same thing. And then don't forget, it could have also been written this way. those interchangeably. Right? Okay, let's see if we can do the same analysis with the dehydration. Can we separate it? Can we go backward until we get to two separate pieces? So I think it's a little bit easier to do that if you could possibly draw the addition intermediate if you're not sure, but I also like to kind of just circle the piece that remained untouched, in other words, the one that used its alpha carbon. So notice that I have an alpha carbon right here to a carbonyl, so that must have been my enolate, right? So the alpha carbon attacked, and that pi bond is where the new sigma bond was. And the carbon and the pi bond attached to it used to be a carbonyl. I'm putting the carbon in that red circle that's in the part of the pi bond. That carbon, when it was added additionally, had an OH on it, it got attacked, and then before that it was a carbonyl. So that gives us our enolates right here. I'll color code it this time so that they match these guys. So that's that blue one attacked the red piece. But it's the same thing, just not charged. Any questions on that? Okay, so because I've been describing these as self-condensations, I'll even write that here. We're going to, of course, advance to the cases that are that do increase in complexity, where they're not self-condensations, they're mixed. So we call them crossed aldols. Now, how does that increase the complexity? Well, it all comes down to who's the enolate, right? Who's the nucleophile? Who's the electrophile? Why doesn't it do it with itself again, have its self-condensation, even if there is a friend nearby, right? So what's going on in that scenario? So I have an example that can undergo a crossed aldol, but we don't want to neglect the fact that the self-aldol is also possible. So here's what I mean by how complicated it could end up being. So we could have, how many scenarios could we really have if we have a mixture of crossed and self? I think I'll color code this because I'm going to actually write them all out. So I'll do the first one in black. We could have this guy be the nucleophile and this guy be the electrophile. Then we could have another scenario, which I'll write in blue. We can have that reversed, because they both have alpha H's, so they could each be the enolate. And I think I did the next one green, so 3. But don't forget our self-condensation possibility. So we could have this one first become an enolate, then attack itself instead of the neighbor, and nothing with that one to play a role, right? So we draw the green product that results from that, and then in red, we could have the opposite. So this one doesn't get the base, this one does, and it becomes the enolate, and it also serves as the electrophile. So because I do not see heat or extended conjugation possible, look at our R groups. There's no heat over the arrow, and our groups are methyl and ethyl, and then we have some H's, no extended conjugation. I'm going to draw just the addition product. So label that here. All right, so the possible addition products. So in black, I'll do case number 1. That's where we let the first one, so propanaldehyde, also known as propanal, react with acetaldehyde, also known as ethanal. So if propanal is the nucleophile, then that's the one I always like to draw first because that means the enolate was here, right? That was the nucleophilic carbon. Then it attacked this one and opened it up. So I need a new bond. And to that new bond, there's a carbon that used to be a carbonyl that now has an OH instead of the carbonyl attached, and whatever R group which was there, which is a methyl. Okay, so that's possible product 1. In blue, we have the reverse. So our second friend gets to be the nucleophile. That means I'm going to draw that one first. As is, just keep that intact. And then you visualize, that's the enolate. The alpha carbon has the negative charge. It's going to attack, so it's this guy. It attacks that one. That one has an ethyl and an H attached, but this ultimately becomes an OH. So, new bond. Oh, I need a blue. There we go. New bond. I'll just draw it down here. And this is as soon as I draw the new bond, the carbon that extends from it is our carbonyl carbon. That carbonyl was converted to an OH. And then I draw in remaining R groups. There's an H and an ethyl. I'm not going to draw that H because we have to get in the habit of not doing that every time. But, you might change the conformation. You might see it all optimized to be a little more linear looking in solution manuals and whatnot. But in any case, you just want that to match. Okay, then I'll predict my green product where it's a self-addition reaction. So I start off with the carbonyl as is intact. However, instead of drawing this piece, I draw a second version of this. So attacks, once again, ethyl and H are attached as well as now an OH. So see, there's kind of a theme here. I think the systematically easiest way to approach these products without drawing a long mechanism every single time, but you need to know the mechanism. It has to be kind of walking through your head while you do it. Is we say, okay, this was my enolate. It has a new bond here, right? New bond here, new bond there. From the new bond, old carbonyl is now OH. Old carbonyl is OH. Then from that carbon with the OH, the rest of the R groups are drawn in. Okay, so 4 is the red, where, let's do that exercise again. We have ethanal is the enolate and the electrophile. Enolate carbon makes new bond. That carbon that it just branched out to has an OH attached, and whatever the R group is, which is a methyl in this case. Okay, so what a mess. 4 possible products. What is different about this type of aldol reactio? Never noticed that type of reaction. 4 possible products. Okay, so this would not be a desirable outcome right? No one wants a mixture of four things. We're not even talking about stereocenters. That's a whole other ballgame. We're just talking about isomers, so that are, constitutionally related in some way. So a crossed aldol reaction is very useful because you want to be able to mix and match two different things, but you want to favor fewer products. So some ways that we could do that. It's very useful when one of the carbonyls has 0 hydrogen atoms on the alpha carbon. What does that mean? It has no alpha H's.
Oh, no.
It cannot be an enolate. You rule out half of those products. It can't be an enolate. So in other words, this is reiterated in full sentence here. When this happens, the carbonyl with the hydrogen atoms is the only one that can be the enolate. And the carbonyl with no hydrogen atoms on the alpha carbon must be the electrophile. So here is a better scenario where we would see that happen. This isn't going to participate in a whole lot of side reactions because this has no alpha H's. The aldehyde H is never an alpha H, right? It has to be on a carbon to be an alpha H. There's no alpha H's here. Otherwise you'd have 5 bonds to carbon, right? So no H here, no H here. This cannot be the enolate. So that means that this one must be the enolate because it does have an alpha H. This one must be the electrophile. So if I want to draw the mechanism, I could fix this so I could draw in the H. I'll put a 2 there, CH2, so I could draw in the third H there. And we'll fill in our lone pairs and form our enolate. Okay, I'm going to let you, since I've done this mechanism a number of times, I'll let you finish the mechanism for practice. Let's use what we know about the mechanism to help us predict the product. So the enolate was ethanal. That's the one I like to draw first. And because I have my bond forming step on the left side, I'm going to keep this whole thing on the right. What does I draw? Because I have to draw new stuff to the left of it, right? Just to minimize flipping around and making things unnecessarily confusing when you're solving the problem, because it's hard enough as it is, right? So I'm keeping it some space to the left because that's where my new bond's going to be. So there, the enolate is drawn as is, new bond, and this new bond is the carbon that had the carbonyl. It was attacked and it became an OH, and we have to decide if it's going to be dehydrated or not. So for now, I'm just going to draw in the other R group. Okay, so should I put an OH here, or considering this R group, should I let it be dehydrated? Dehydrated. So instead of drawing in the OH like I did several times in the last example, I'm going to mentally kind of walk through and say it's going to lose the OH as water to make the conjugated pi system here, right? Alpha beta unsaturated carbonyl. Okay, so there's your product of a crossed aldol condensation that can work very efficiently because you have no alpha H on one of them, so you don't have that possibility for so many mixtures. There are other ways to favor it, so you might say that limits us a lot, right? Because you have to make sure there's no alpha H on one of them. You can actually still favor one side of a crossed aldol series of products if one H is more desirable to pull off than the other one. In other words, it would be more acidic. So we'll do that example next. So another way that we can use a crossed aldol by design in a very efficient way is if one of the alpha H's is significantly more acidic than the other carbonyl compounds. So of course, the one that's more acidic is the one that will be removed to form the enolate, which leaves the one that's less acidic to be the electrophile. So case in point, ethanal, no alpha H here, but there's alpha H here. Then we have this diester, which has an alpha H there. So they both have alpha H's. Which alpha H is more appealing to the base? The diester, because it has the resonance stabilized conjugate base, right? Okay, so that's our enolate. All right, do we want to do one more mechanism, or do you guys feel like you want me to walk through the product, which is more helpful? Walk through the product? Because we've done the mechanism a number of times, but it's not a bad idea to, I leave it open if you need it, but you want to be able to use the mechanism to walk through to the product. So we have our base, takes that off, that's our enolate, so we're going to have a minus there. That means all of this framework stays the same, so I'm going to draw that. So in comes, what you do where the enolate was, is new bond. So since this is a pretty conjugated system, right, I expect to dehydrate, right? So I'm going to plan for that new bond to actually be, or that's the one that gets dehydrated. I'm going to plan for that. And then you draw your R groups on. Instead of drawing OH, I drew an alkene because I have more conjugation on this side in addition to what was already there for an alpha beta unsaturated carbonyl. Okay, so new bond that would have opened up to an alcohol, but I've gone a little faster, letting it go to the dehydrated product. Now on the new bond to the new carbon that I'm just adding, I need to draw my R groups, and I had an H, which I'll draw just for clarity this time, and a methyl. That's from the ethanal. Okay, so far, cross aldols are still a little bit limiting because they really only avoid a statistical distribution of products if something favors one to be the enolate over the other. Like for example, it's impossible for one to be the enolate because there's no alpha H's, or in this case, you are able to find an enolate that would be significantly more acidic and still give you the product you want. That's not always the case. Sometimes we want a product where we don't have a significant difference in acidity. We also have to have alpha H's on both. When that's the case, of course, chemists have figured out the workaround, which is what's called the directed aldol. So instead of mixing everything in one pot and letting the base pick, and if there's no preference between them, the base is statistically likely to pick both of them as the enolate, you force only one to be the enolate by doing it in steps, right? So the one you want to be the enolate goes first, and then intentionally use a very strong base. Why a strong base? So LDA is a very, very strong base. It needs to be strong to avoid equilibrium. That we want the equilibrium to favor the right side, the deprotonated side. If it was a weak base, you'd have more concentration of the original not being an enolate, right? So you want a strong base to favor the enolate side of the equilibrium so that it stays on the enolate side. Then while it's an enolate, you're ready to do step 2, which is to throw in the carbonyl compound you wanted to be the electrophile. So you need to use LDA. You don't just use an EO base. You need to use one that's been described as a strong base. Okay, keeps it low temperature as well, just to avoid any enolate reacting with itself, but stoichiometry also controls that. If you make sure it's 1-to-1, then you can also encourage that it fully goes to the enolate first. So I'll draw out this mechanism just because this is a 2-step process, even though it's really the same idea. So LDA is lithium diisopropyl amide, meaning that we have negatively charged charged nitrogen, and amine, or we get the "ide" sort of ending. So some people would pronounce it amide. Some people will say amide. So it's kind of just a preference. You kind of hear regional preferences for that. I think amide is probably technically better because we say oxide, right, or chloride when we have an anion. But then when you get into amide, there's some regions of the world that say that for the carbonyl amide. They say amide instead. So it can get confusing talking to someone from a different area, that whether they're talking about the amide, like in peptide linkage, or deprotonated amine. But at any rate, it's spelled the same. Amide, amide, but lithium disopropyl amide or lithium disopropyl amide. That's our base, very strong base, takes off the alpha H. So to draw the mechanism, I'll extend the bond for one of them on the methyl and form our enolate. So this is step one. Along comes step two, once you feel like the reaction has been given sufficient time to complete, and we add in the desired electrophile. You might notice these R groups. This was that one that gave that big messy distribution before because it was not directed. So this is directed. All right, so now our final product, we'll have the enolate as drawn, and then, so that's my enolate to start with. New bond. Okay, the new bond ends with a bond to the carbonyl oxygen that used to be there that's now an OH, and then throw in your R groups. So when you clean that up, your answer would more likely resemble something like this. So we would have had alpha beta if it dehydrated, but instead we have a beta hydroxycarbonyl, and the R group is a ethyl. And then I didn't draw in my implied hydrogen on the carbon with the alcohol. So that's the addition product, right? And so that favors just one of the many that would be possible if you hadn't directed it to do so. So the directed aldol is really useful. Any questions on that one? We're going to try to think backward using the same thing with a retro, because you want to be able to fill in, a step backward as well as a step forward, not just predict products, but say that's what a chemist does. They're told to make something, and they say, what starting materials do I need for that? Okay, so now we are in a mixed starting material scenario because this is a directed aldol. So clearly there's only one cyclohexane ring. That means it's a crossed aldol situation. Who used to be the enolate? Whoever has the carbonyl still, right? So I know that this carbonyl has two alpha H's, but only one has an attachment to it. That must have been where the new bond was, right? So that means this chunk was the enolate. And this piece was the electrophile. So the question says to propose a synthesis of the molecule to favor that, right? So then we want to do the directed aldol because this is one of those scenarios where we don't have a significant difference in acidity. However, nice nicely enough, we actually could have, unless this, right here, this one, this guy has no alpha H. So a crossed aldol would also work. So if we wanted to do it directed, we'd start off with this one and then make the enolate, then separately, separate step, throw in this one. But because it has no alpha H, crossed aldol would also work as well. So I'll write directed just because we were just practicing that. So something like this. 1 LDA CHF, negative 78 degrees Celsius, and 2, throw in your desired electrophile. And then we arrive at our product. Okay, any questions on that? Yes?
So if you were trying to get it to attack itself, you just wouldn't add step 2?
You'd also have to change the stoichiometry. Yeah, so if I wanted, that's a good question, Branson. What if I want something like, let's do this one, OH, and then at the carbon, so this is the carbonyl carbon, we would have, I'm off, thank you. I have like an infinite, I need to get used to that, my space is like infinity, and at some point it goes off. Okay, so, which is good and bad. What if we wanted that? A self addition. So how do we do that? So you'd have to say this plus your base, right? But if you want to make sure that you can do the self addition, you want to avoid, you don't need LDA, it's better to do a weak base. So hydroxide is not usually our definition of a weaker base, but weaker base than LDA. And then you want to do half an equivalent. Right? Because if you do a 1-to-1, or in other words, 2 or 2-to-1, right? That's the same as saying half an equivalent. You want half of it to remain undeprotonated, right? The other half to get deprotonated. So the equivalents also matter if you're trying to do a self versus directed, right? Directed, we would do 1-to-1 ratio because you want everything to be the enolate before you add the next step. So yeah, good question, because that's a distinction that is going to, come up as you practice. How do you favor one route or the other? Okay, so among, I have no idea why, but I always think intramolecular ones are particularly fun. So we get to do that with a vengeance at the end of this chapter, which might be why it's my favorite chapter. We do so many intermolecular reactions, and so we're just going to kind of scratch on the tip of the iceberg of them today, but they'll play a major role in some sequences of reactions later. So we'll start off with a simple one. Remember, we like to do intramolecular reactions when we form a desirable ring size. Usually 5, 6, or even 7. But 6 was the preferred ring size for the tetrahedral carbon. So 1 above or below still happens quite easily, but 6 is really the goal. So you'll always favor 6. You'll have choices to make. That's why you want to keep that rule in mind when you start counting your carbons. If you count 5 versus 6, usually you go for the 6. Okay, if a ring of that size can be formed, it usually results in the dehydrated product, but there's no nice conceptual reason behind that. So when I want to kind of encourage you to do that, I would do something like that and add some heat there, right? Because it's kind of assumed in a lot of these examples that it just keeps going, but it doesn't tell you why. So I'll usually add some heat just to make it really obvious. However, and if someone forgot to dehydrate, honestly, the hardest part was getting to the addition step. The dehydration is a 211 reaction, it's an elimination. So if it was like one of those big predict the product problems that was 5 points or something, it would still be 4 of the 5 just to get to the aldol addition. The dehydration is the last step. The hard part's getting the aldol right. Okay, so for example, we want to do an aldol reaction here. How do we know that? We have a carbonyl compound with alpha H's. We have a base. I'll go ahead and throw in some heat. And we only have 1. Nothing else is added, but we have 2 carbonyls, which means it can do an intramolecular, right? Aldol. So you have to start counting and make a decision about which way is the best way to go. So if I look at all my alpha H's, I'll just label them here, alpha, 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 alpha. So I'll call this 1, 2, 3, 4, just in case I have to refer to them later. And I'm gonna start counting from 1 alpha H to a carbonyl. So for example, I could say, well, I can make an enolate here. And then it can't attack right next to it, but maybe it could wrap around and attack at that 4 position. What size ring would that be? 4-membered ring, right? So that's not ideal. Let's do a different numbering system. Let's try it from the end. What if I say, how about I make the enolate here from that alpha 1? And so then I can attack the opposite carbonyl down here. Let's see what our count turns out to be. So 2, 3, 4, 5, 6. Now that's more like it, right? 6-membered ring. And because it's symmetric, you would kind of see it works both ways. So I'm going to aim for the 6-membered ring. So that means I'm going to be taking everything off here. So I'll draw in my H. We can attack and leave behind the electrons. Okay, so now it's going to do an intramolecular attack. Attack, open, and it doesn't hurt to keep up the numbering. So 1, 2, 3, 4, 5, 6. It helps a lot actually, just because you have to fill in your substituents once you make your ring. So my starting point every time I do intramolecular is to go ahead and draw the ring of the correct size. And then number the ring. So let's see, I have, if I just wrap this around, then I'm actually kind of going counterclockwise, so I'll just keep it the same. 1, 2, 3, 4, 5, 6. Okay, so then I fill in what I know that didn't change. On 2, I had a carbonyl that was unaltered. On 6, I have to have a methyl still. But I opened up to an O-. So it looks something like that. Then I need to neutralize. So notice in the ring, I still make that familiar alpha, beta, the beta position, hydroxy ketone, right? So that's a sign that I did my aldol correctly, my addition. And that's actually the hardest part, is getting to there. To make the decision to dehydrate is fairly simple, because you always have to go in the direction of the conjugation. Like I could have taken off an H here and make this alkene, but that's not conjugated. I'm always going to make the alpha beta. Take off this H and take that OH off to there's water, and do an alpha, beta, unsaturated carbonyl. And then I have a methyl still there. Okay, any questions on our intramolecular ring closing reaction? Yeah, when you form the ring, you should still see the same pattern, it's just with itself. Okay. So we've been focusing on doing this reaction. So the good news is this was kind of the hard part of the learning curve. The next several reactions are actually parallel to these. They're the same underlying concept. So if you're practicing these and you're following this, the next actually should make a lot of sense because we're only expanding the starting material to beyond aldehydes and ketones. We've only done aldehydes and ketones. So remember, aldehydes and ketones are carbonyl compounds with no leaving group. We will expand this to include mostly just esters, honestly, so that even keeps it simpler. So usually OR. So remember, if we have a leaving group, we do the whole attack open close kick scenario, right? We do attack, I'm going to do the faster version, open, close, kick. So then we get our nucleophile replacing the leaving group, and I'm adding all this extra stuff because the focus of this section is what's happening at the alpha H position, right? So that's what we're going to do now. We're going to take that old attack open close kick mechanism and combine it with what we know enolates can be a nucleophile. So in other words, if our nucleophile is an enolate, instead of attack open protonate to get the beta hydroxyketone, or maybe even protonate, then it leaves to form the dehydration product, it's going to do attack open close kick and maintain the carbonyl that was there. So it looks a little different because you will keep carbonyls on both of them. So for example, Claisen reaction, which is named specifically, usually when we have this is an ester, and then we have our base, so I'm just kind of generalizing this. All right, so we take off our alpha H, make our enolate. I'm going to define Z as OR just because that's the Claisen. The Claisen way is to have like OET or OME, but you know, in theory, it could work with other acyl derivatives. From that chapter, that massive chapter in the system, the carboxylic acid derivatives. Okay, so we make our enolate. This is our generic template. And then it can attack another one. But instead of doing the attack open protonate, so we have attack open, I'll draw this whole step out this time. So that carbonyl's here, we still have our two R groups. Okay, so enolate stays intact as usual. New bond, carbonyl that opened is here. So far the same, because up until now we would protonate next. So it's after this that it changes. Okay, so new bond, we have our OR, we also have our R groups. It's a lot to think through drawing that all out, but it's when you see that the mechanism is really the same, your focus has to be just on making sure you don't drop carbons and connect them incorrectly. That's usually the biggest pitfall. close, and remember that esters can kick off that alkoxide group in basic conditions. So close kick. That leaves us with, that part's the different step from what we did previously. So before we protonated, we had an OH, and then we had a possibility of dehydrating. That doesn't happen anymore. When we close kick, you close back to a carbonyl. So we have our two R groups here. New bond, carbonyl, and then our R groups again. So I'm going to box this. That's different looking than what we've seen before because the last step of the mechanism is the same. So we do not have a beta hydroxycarbonyl. We do not have an alpha beta saturated carbonyl. We have a 1,3 dicarbonyl. So that's the pattern you will see when you start with an ester. You get 2 carbonyls at the end, at the 1,3 substitution pattern. Oftentimes, there's one that we see frequently, which is this scenario, which is also called a beta keto ester. How could we describe that? So to the ester, here's our alpha beta, right? So with respect to the ester, at the beta position, there's a ketone. So it's a beta keto ester. The more generic term would be 1,3 dicarbonyl because there's not a guarantee that the beta position is always a ketone. It might be a aldehyde or something. However, that's what that functional group implies, beta keto ester. So that happens from a Claisen reaction. So that's a name reaction. But the only difference it has from the aldol is that it keeps the 2 carbonyls.
Professor,
Yes.
can you say the 1,3 thing?
Yes.
Dicarbonyl.
Yeah. So I know the mechanism's important for us to follow it. So I spelled it out in great detail in the box. Now I'm going to do more of a mini mechanism because if you're, I know with myself even from sitting a long time drawing mechanisms, I'm starting to kind of get deep into the forest, and then I don't see the trees anymore, right? So you're just going down a path with a lot of detail, which is important to do, but sometimes the problem is to kind of get to the point and get to the product. And so that's when understanding the detailed mechanism helps you if you can follow through with a more miniature mechanism. So in other words, I'm going to say, okay, I'm not drawing my acid-base steps. I'm going to go straight to my enolate. I know that's what I make. Okay? So after step 1, I would have something like this. So I have my alpha carbon deprotonated. Okay, then step 2 means that, step 2 is neutralizing. Before I'm done with step 1, I have to, notice it says 2 equivalents. Like I said, the equivalents are important here. That means that half equivalent, in other words, is base. So it's a 2-to-1 ratio. So that means only half of these are the enolate, the other half stay this way, and that's to promote the self-attack that Brandon was asking about earlier, like how can you promote that? So equivalents help with that. So here we go, doing a fast mechanism, attack, open, close, kick. All right, now drawing that product. Enolate stays the same, and since my new bonds occur to the left, I'll push my enolate over to the right so I can make room on the left. Then in comes the new bond. New bond to that carbon. That carbon had a carbonyl and it regained the carbonyl. Attack, open, close, kick. The carbonyl came back. What was on that carbonyl? OET, which is our leaving group. So I don't draw that, but I do draw the methyl. There's our beta keto ester. That is classic Claisen, telltale sign of Claisen going on. All right, because our product is an ester, it's important for these to match. You want to match your base with your OR group, because otherwise you have to deal with transesterification products as well, and that's a big mess, right? So match ester OR with base OR minus to avoid transesterification. Unless that's actually what you want to have happen as well as applies in. Okay, so the Kleisen, the good news is about the Kleisen is that it's kind of, I think it's a little bit of a brain break before we get into the harder reactions in the chapter, which you gotta prep yourself for that Robinson annulation near the end. That one's a doozy. Puts it all together and relies on this information. But the Kleisen follows in parallel with the aldol. So we just did a self-Kleisen. We can likewise do a cross-Kleisen. But I'm not gonna do all the statistical variations again. We'll just point out what makes it useful to give us control, right? So if we want a cross-Kleisen to be useful, then we want one of our esters to possibly have 0 alpha H's. Okay, once again, the ester with hydrogen atoms on the alpha carbon is the only one that can be the enolate. And the ester with no hydrogens on the alpha carbon must be the electrophile. So this will give us an exercise with cross-Kleisen. So we have alpha, no alpha, must be the enolate. Right, because there's our alpha H on that carbon. Okay, so I'm just going to go straight to letting it be the enolate to kind of save some time with mechanisms. And this one does our attack, open, close, kick. So my product keeps the enolate intact, new bond, carbonyl stayed intact because it opened and it reclosed, lost the OR, only have an H left. Kleisens are actually easier, I think, than aldols, because you don't have to sit there and decide if it's going to dehydrate or not. You're done. You have your 1,3-dicarbonyl. Simple, right? It just has the close kick step that's different. Okay, so just like the aldol, you can also exploit the ability of one to be more acidic than the other. So this, in the Kleisen scenario, this most often comes up with one of them has to be an ester in order to get the close kick. But the other one is often a ketone. So who's more acidic, for example? These both have alpha H's that can be removed to make an enolate. Who's more acidic, the ketone or the ester? So another way to phrase that is here's my base, and if the H is going to, when it comes off, going to make a stable conjugate base, if it's going to make a stable conjugate base, then it has a bigger delta plus on it, right? That means it's going to be drawn to the H with the bigger delta plus. So who has the bigger delta plus? Well, ester, the difference between ketone and ester is our group right here is instead an OR. What does the O do? Donate electrons. What does that do to the nearby electron density? It pushes electron density away from it, right? It's donating electrons. If it can donate electrons, so I'm only drawing this to show that it's an electron donating group. if OR is more electron donating than R, what does that say about the delta plus on the H of an OR group? Yeah, it's actually donating electron density, so the magnitude of the delta plus is actually smaller. So it would be better to draw this a bit really tiny, and to draw this one, just to overemphasize it, is really big. Right? So smaller delta plus on that H. The base is less attracted to it. So electron donating group, therefore alpha H nearby is less acidic. So that means that our only enolate option is going to be, I have to fill in the blanks here, kind of trying to work through that first. So in this case, the ketone will be the enolate, and the ester will be the electrophile. This is our electrophile, and this is our enolate. All right, so let's walk through the mechanism. Enolate means I have a minus here. Attack, open, close, kick. Let's see if we can replicate that as we draw. Since I have a lot of words up there, I'll make this one the one below it, the enolate right here. So enolate stays intact. I'm going to put a new bond there. New bond. Okay, I opened and closed the carbonyl, so it stays there. I kicked off the OR, so the only thing left is that methyl that was there. There's my 1,3 dicarbonyl. I mean, usually it's drawn a little more upright, like this. These are the same, right? So if you looked in your solution manuals, for some reason, that's the way we like to read those things left to right, not read the molecules going down vertically. But they're the same thing, just slightly rotated. Whatever helps you draw it is really what matters. It doesn't have to be re-rotated. Okay, so I've covered self-Claisen, cross-Claisen. The last scenario is intramolecular, which I will leave that as a warm-up. Same idea, nothing new. So we'll do that when we get back. To get ready for workshop. So I better go head up and see if I can get some laptops on hand. Good luck studying and keeping up with this stuff.